Okay, so here we are again. This is I think it's the first talk of the seminar series of the Institute of Astrophysics after the Christmas break. And today we are very glad to have Antonio Pensabene. Antonio is a postdoctoral research associate at the Department of Physics at University of Milano-Bicocca. Antonio got his bachelor and master degree in science at Università degli Studi di Firenze. I hope my Italian is
Yes.
sufficiently intelligible. I don't spend as much time in Italy as I should, but yeah, I hope it was understood. And Antonio was he moved to INAF to get his PhD at the Astrophysics of Space Science and Observatory. And since 2021, he's a postdoc at Milano-Bicocca. Antonio is an expert in galaxy evolution, in particular on the topic of high redshift star-forming galaxies, and specifically also quasars, where he studied their interstellar medium, their intergalactic medium, and circumgalactic medium. And today he's gonna talk about that aspect of his research about supermassive black holes. So, Antonio, whenever you want, the floor is yours.
Okay. Yeah, thank you very much, Tanio, for inviting me here. It's a real pleasure to me to give a seminar at your institute. And thank you also for the very nice introduction. So as Tanio was mentioning, today I would like to show you some recent advancement regarding what we are learning about the assembly of early massive galaxies and also their convolution with the supermassive black holes and also the critical role of the large-scale environment in the assembly of these primordial massive galaxies. The results that I'm going to show you has been made possible thanks to the effort of many people. And here I listed the main names of such people, in particular Sebastiano Cantalupo, Roberto De Carli, but also many, many others. So, despite significant effort in the fields, there are still a number of questions that are still unanswered in understanding the assembly of early massive galaxies. In particular, what I will try to tackle in my talk are questions regarding the interplay between star formation and black hole activity during the early stages of galaxy evolution. In addition, any real advancement to understand how the galaxies form and evolve within the cosmic web need to pass through the question on how do galaxies get their gas from the surrounding medium and how the accreting gas affects the galaxy gas content. In addition, there are growing evidence about the critical role of the large-scale environment in shaping the formation and the assembly of early massive galaxies. And to attack these questions, we need now to bridge the scales, combining multi-wavelengths observation using the most powerful facilities available today, such as JWST, ALMA, and VLT Muse. And therefore, we need, it is urgent to bridge these scales from the physics of the interstellar medium within galaxies to their large-scale structure, passing through the properties of the gas in the immediate surrounding of massive galaxies within the so-called circumgalactic medium. And what I'm going to focus about in my talk are are is the way to attack these questions using quasars at high redshift. And for high redshift, I mean redshift greater than 6. Indeed, quasars are great cosmic laboratories. They are believed to be the progenitor of today's most massive galaxies. They are among the most luminous sources in the universe, with volumetric luminosity that can be greater than 10 to 12 solar luminosity. They are powered by a rapid accretion of matter onto their supermassive black holes that are accompanied by intense episodes of star formation in the host galaxies. And today, what we can do, thanks to the most powerful facilities that we have, is to we can really image this powerful laboratory down to the cosmic dawn, but with some difficulties. Here I report a typical spectral energy distribution of a quasar's redshift greater than 5, in which you can clearly see that the majority of the energy budget is actually dominated by a component related to the central engine of the quasars, such as the accretion disk. And therefore, if you use observatory in the rest frame UV, such as the Hubble Space Telescope, we are currently unable to image the host galaxy of quasar, since it is completely outshined by the powerful emission coming from the central region. With JWST, we have now more chances to detect the whole stellar population of these galaxies, even if also in this case, modeling the point space function of the quasars is relatively challenging, but we can access the ionized gas phase surrounding in their surroundings. And therefore, the most optimal way to access the host galaxy of a high redshift quasars is still in the far infrared wavelengths, using instruments such as ALMA and NOIMA, and therefore study the coal, gas, and dust in this powerful object, as well as the gas kinematics through spatially resolved observation. The study of high redshift quasars is also important to place constraint on the black hole galaxy convolution. Indeed, there are growing evidence about the fact that high redshift quasars seems to host overmassive black hole with respect to what is observed in the local universe, and this is extremely important to probe the onset of such black hole galaxy relation. In addition, the discovery of quasar at increasingly high redshift can help to put constraint on the different scenario regarding the formation channel of the first supermassive black hole. Also, quasars are important to study their surrounding environment. Indeed, they act as a flashlight, illuminating the surrounding gas and ionizing it, then recombines, emitting a series of emission lines, the most bright of which is the hydrogen Lyman alpha line. And thanks to these processes, by targeting quasars, especially at cosmic noon, using instruments such as VLT Muse, we can now study in great detail, cosmic wave filaments. And here I report a recent work by Davide Tornotti, working here at University of Milano-Bicocca, in which in this work they were able to trace these cosmic wave filaments traced by Lyman alpha emission, connecting a quasar pair at redshift 3. In addition, we can also study the intergalactic gas using quasars as a background sources, combining with absorption spectroscopy. In this case, we have just one-dimensional or at best two-dimensional information, but by looking at high redshift quasars, the light that pass through different patches of neutral medium toward the observer imprint their features in the as absorption lines in the spectra of the quasar, producing features like this Lyman alpha forest that can be used to probe the structures of the IgM across the cosmic time. Last but not least, high redshift quasars are believed to reside in the most dense structures of the early universe, and therefore they can be used to probe this overdense structure to pinpoint the first galactic overdensities. And indeed, here I report just a couple of examples, but the literature now is full of this kind of results of overdensity of some millimeter galaxy discovered in the surrounding cosmic noon quasars, and also revealed, for example, through Lyman alpha emitter. Here you can also see the nebula surrounding the quasars and the population of Lyman alpha emitter surrounding it. So now that I set the stage of my talk, I would like to show you how my talk will be subdivided. So I will start by showing you some recent advancement that we obtained by using multi-line surveys in the some millimeter, but also some recent observation taken with JWST that is allowing us now to put constraint and characterize the multi-phase interstellar medium in quasarous galaxies down to redshift 6 or above. I will then show you some also recent very interesting results about the large-scale environment of high redshift quasars, highlighting the crucial role of the cold gas in the assembly of those early massive galaxies, and also some pilot program that we are now pushing forward in order to study the IgM-CGM galaxy Byron cycle down to the innermost scales using a high resolution VLT Muse, JWST, and ALMA observation. And finally, in the very last part of my talk, I would also like to show you some recent work that we are carrying on using that combine absorption spectroscopy of background quasars with the some millimeter survey with ALMA to study the gas structures around dusty star-forming galaxies across the cosmic time. So let's start with the first part of my talk about the characterization of the ISM in redshift 6 quasarous galaxies. So we know that the interstellar medium is a very complex environment that is composed by multiple phases, and therefore to obtain a complete pictures of this very complex environment, we need to target a specific diagnostic that are associated to the different phases of the ISM. And this is now possible thanks to ALMA to do this kind of study at very high redshift. And this is what we have done in the past by capitalizing on this serendipitous discovery of quasar companion galaxies at redshift about 6 that reported by this work by Roberto De Carli in 2017. And the companion galaxies that are located, here you can see some images of these companion galaxies that are located in the close proximity of these quasars, do not show evidence of strong AGN activity, and therefore this system allows us to study the interplay between star formation and black hole growth on the physical properties of the ISM in these massive galaxies. Here you can see some more recent observation on a couple of this system, in which you can clearly see the now spatially resolved images of the quasar host and their companion galaxies, also in some cases showing tidal features. This is a merger in progress. Indeed, this was the two system on which we focused on in this ALMA survey that we published back in 2021. This was the first ALMA multi-line survey of redshift greater than 6 quasar host with nearby non-active companion galaxy. And with ALMA, we targeted the two systems that I showed you before in multiple line diagnostic associated to different phases of the ISM. For example, you can see here the nitrogen 2 that is mainly come from the ionized gas phase, but also high JCO line that are associated to the high dense, high temperature molecular gas. In addition to atomic fine structures and molecular lines, we can now probe also the dust continuum of these galaxies, and this is the typical situation that you have in some millimeter observation, in which with this multi-band photometry, we are now able to put constraints on the Rayleigh Jeans tail of the dust spectral energy distribution. And to put a tighter constraint, we actually need to go we need to use higher ALMA bands to cover the part of the dust SCD which is more sensitive to the dust temperature. But unfortunately, these bands suffer from from a very bad atmospheric transmission. So we can now combine the information coming from the continuum and the line by using models of photodissociation and X-ray dominated regions. And to do so, we can use codes such as cloudy that simulate a radiation fields coming from an example for example, a young stars or X-ray radiation field from an AGN impinging on a slab of ISM. And these kind of codes are able to solve the radiative transfer equation across the medium and provide you with the line intensity at the surface, at the opposite surface of this gas medium. And we can therefore create a diagnostic tool and combine it with the observed line ratio, as we have done in this case. For example, here we used the C plus over C1 line ratio, which is turned out to be a powerful diagnostic tool to distinguish the PDR versus XDR scenario. And by combining also with the information from the continuum, such as the total infrared luminosity, we were able to place constraint on the strength of radiation fields and also on the a rough constraint on the average value of the total hydrogen gas density. We can also study the CO spectral line energy distribution by combining different CO detection. And here you can see how quasars at high redshift shows relatively bright high JCO lines, which, as I was mentioning before, are lines associated to highly excited gas. And indeed, the radiation from the quasars is able to excite, to penetrate much deeper into the molecular clouds, therefore exciting this high JCO line. And the situation appears to be different if we look toward more normal star-forming galaxies. And using cloudy model, we can try to reproduce this kind of CO spectral line energy distribution. You can see again model in photodissociation and X-ray dominated regions. And by using this model, we can estimate the contribution on the observed CO emission coming from the PDR and XDR dominated regions. And as you can see, for one of our quasar, we were able to estimate that 90% of the emission coming from low J CO lines are associated to PDR, to ISM in PDR regime, while a high J CO line need XDR regime in order to be fully reproduced. And we can also place constraint on the density of this medium and on the strength of the local radiation field. And today, thanks to the unparalleled effort of JWST, we can go farther. We can now start to study the ionized gas phase and combine information of the ionized gas phase with information coming from ALMA. And this is what we have done in this recent work published by Roberto De Carli last years, which we studied actually one system that was also part of our ALMA multi-line survey. You can recognize here the companion galaxy, the bridge connecting the quasar host with it. And we mapped this merger using JWST near-spec IFU observation. And by using cloudy model, we studied the photoionization condition of the ionized ISM phase, and also we placed some constraints on the stellar population detected with JWST. In addition, we can also now get very extremely high signal-to-noise detection of Balmer hydrogen line, such as H-alpha, H-beta, that allow us to place more Tiger constraint on black hole mass and compare such estimate with a single epoch virial mass estimated through lines such as magnesium 2 or carbon 4. And we also published this result in this recent work by Federica Loiacono last year. Moving forward on the characterization of the molecular gas in Redshift 6 quasar host, I would like to show you some innovative pilot program that we started in which we targeted a bunch of far-infrared luminous quasars at Redshift 6 with the NOEMA interferometer. And we targeted the water vapor lines. So water vapors can be very bright, even brighter than a high JCO line in these infrared bright sources that are interesting diagnostic on the warm and dense phase of the ISM. Indeed, the excitation of these lines is very complex because it's due to both collisions in the cold phase and from infrared pumping due to the radiation coming from the dust. And by combining information from multiple H2O lines, using again relative transfer code, we were able for the first time to place constraint on the temperature of the warm-hot dust component and on the characteristic of this warm dense phase. And we are planning to do a more statistical analysis of the warm dense gas in these massive galaxies at cosmic dawn with some recent ALMA program that is doubling the sample of far infrared bright quasars with multiple H2O lines detected. What I show you now are basically spatially unresolved observation and to get the average, the spatial average physical properties in these quasarous galaxies. But thanks to the exquisite capabilities of ALMA, we can also perform spatially resolved studies of quasar host across cosmic time. Indeed, here I show you a work in which we basically we capitalized on a high resolution observation from the ALMA data archive, and we collected a large sample of quasars from redshift 4 to 7, in which we studied in detail the gas kinematics as traced by CO or C+ line emission. We can now model these gas kinematics by using a fully Bayesian method, taking into account the instrumental effects such as the beam smearing, which is one most important effect that we need to take in account when we deal with low resolution observation. And by doing this kind of analysis, we can now obtain robust measurements of the dynamical mass of this quasar host that can be compared with the black hole mass obtained with other method, and study the onset of black hole galaxy relation at high redshift. In this work, we reinforce the idea of how high redshift quasars seems to host over massive black hole with respect to the situation observed in the local universe. And these results has been also supported by various work in the literature that find similar trend, while recent JWST observation targeting low luminosity AGN actually are finding different results. And this is something that needs to be still investigated, because this kind of studies are affected actually by strong selection biases and also by uncertainties related to the different traces of the galaxy mass that is employed to study this kind of relations, and of course to the systematics associated to the estimation of black hole mass at high redshift. Okay, let's now move on the surrounding environment of high redshift quasars. And the results that I'm going to show you are mainly focused on cosmic noon quasars at redshift about 3, near the peak of galaxy and black hole formation. So as I was mentioning before in the introduction, quasars act as a flashlight, illuminating the surrounding gas, then recombine, emitting Lyman alpha radiation, which is the brightest line that we can observe with instruments such as VLT Muse. Therefore, over the year, people started to found ubiquitously these giant Lyman alpha nebulae surrounding cosmic noon quasar. And here I report just one work showing a beautiful example of these gigantic gaseous structures extended on hundreds of physical kiloparsec. And some of them also shows very peculiar morphology, such as filamentary structures. And using very deep mosaic VLT Muse, a recent survey targeted this system called NQN1, enlarging the field of view and going much, much deeper. And the result of this survey was the following. This is the largest contiguous cosmic wave filament found so far in Lyman alpha emission, converging toward a massive node in the proximity of this hyperluminous quasar at redshift 3, sorry. Here you can see clearly filaments of intergalactic gas, and this gigantic structure is extended on at least 4 co-moving megaparsec scale. And on the right, you can see this optical broadband image showing that this structure hosts one of the largest overdensity of galaxies ever found so far. All these yellow squares are Lyman break galaxies selected in the field, which are embedded in this nebula, including a population of X-ray selected AGN, indicated in red, which form toward the core a unique X-ray AGN triplet. Therefore, this is a unique laboratory to investigate how massive galaxies form and evolve within the cosmic web. However, even if these rest frame UV observations are extremely deep, part of the galaxy population can be still missed due to potential dust obscuration. What we have done is therefore to start a multi-wavelength observational campaign toward this field, and I will briefly show you what we obtained in the sub-millimeter band using GALMA. Here in this animation, you can see again the nebula that is appearing in the background. That is the JWST NIRCam snapshot. And with ALMA, we mapped this field in order to unveil the population of dusty star-forming galaxies and gas-rich galaxies selected through their CO emission. And we found indeed a huge overdensity of CO emitter. Here you can see the CO lines associated to the galaxies detected in the field. At the top is the quasar host. Another interesting object located in the proximity of the quasars, that really here at the center, and all the other galaxies located in a narrow redshift range within 1,000 kilometers per second with respect to the quasar system. These galaxies are typically gas-rich objects with molecular gas masses up to 5 times 10 to the 10 solar masses, and are very dusty. Here I show you this example perfectly showcases the critical role of sub-millimeter imaging toward the high redshift universe. Here a CO 43 detected galaxy completely undetected in the rest frame of UV in the news white light image, and is appearing toward redder wavelength in JWST NIRCam. And to study what is going on in these systems and to investigate the role of the large-scale environment on the assembly of massive galaxies, we studied the CO luminosity function, which is basically the number count of galaxies as a function of their CO luminosity, and we compare it with that measured in blank fields as obtained by surveys such as ASPEX or another NOEMA survey toward the Hubble Deep Field North. And our CO luminosity function is shown in red and yellow. And as you can see, there is a clear effect in terms of normalization, indicating that there is a huge overdensity of galaxy in the field. But we also see an additional feature, which is a flattening toward the bright end of the CO luminosity function. We interpreted this flattening as a further excess of more massive galaxies, and probably due to a large amount of molecular gas that is applying the star formation in this field, and somehow accelerating the assembly of the more massive galaxies due to the large concentration of gas. The overdensity in the field in terms of CO emitters is at least 15, but it increases faster, reaching values of 100 as long as we take in account only the most massive galaxies. We found evidence for a virialized protocluster core, as shown by this phase space diagram, showing that this galaxy group is inside the envelope of a escape velocity for a core, for a virialized core with a mass of at least 2 times 10 to the 12 solar masses and a virial radius of 100 kpc, while the entire structure seems to be not still virialized, and therefore we are maybe looking at multiple structures that are starting to collapse toward this core, and therefore this field is probably a protocluster information. Overall, the overall gas molecular gas density is at least 1 order of magnitude higher with respect to the observed trend in blank field, and similar to the most massive structures at later times, such as the spiderweb protocluster. We also acquired high resolution observation with ALMA, targeting the central part of this structure. And I would like to show you some very interesting results that we obtaining by analyzing this ALMA data. So if we look toward the hyperluminous quasar, here you can see the JWST NIRCam snapshot of 3.2 micron, in which you can clearly identify the extremely bright emission from the central quasar, but also the presence of an additional source located 1 arcsecond south to the quasar. Here you can see also the quasar PSF subtracted version that reveal more clearly the presence of this source. That is then, of course, very well detected with ALMA in the 3 millimeter dust continuum. You can clearly see that this object is located just 10 kpc south to the quasar, and it is exactly at the same redshift of the quasar. If you look at the gas kinematics, we can now see that while the quasar host shows a very highly perturbed kinematics, as evident from their CO43, as traced by the CO43 line, the companion galaxies exhibit an extremely smooth velocity gradient. This is a massive galaxies. We modeled the kinematics using 3D Barolo that allow to model through tilted rings method the kinematics of also low resolution observation, and we found a dynamical mass which is at least 2.5 times 10 to the 11 solar masses within the inner 4 kpc. And interestingly, this object has a very high rotational support, which is at least 10. And this is consistent with the evolution of turbulence in galaxy disks across cosmic time, but for isolated galaxy disks. While this object lie in the very proximity of hyperluminous quasars, with a bolometric luminosity of at least 10 to the 48 erg per second and a black hole mass of 10 to the 10 solar masses. We also found evidence for the presence of a possible tidal feature in the CO43 line of the quasar host that may indicate that this galaxy is actually disturbed by the presence of the more massive companion, or an alternative scenario is that actually we are looking at a massive molecular outflow that is expelling gas from the quasar host. But this is not the only surprise that we found in this field. We also find additional surprises that I would like to show you now. So if we go south to this field, this is what we found. We found this very bright galaxy that seems to be very extended, even if the mosaic ALMA resolution were designed to do not resolve the emission of galaxies. Indeed, the angular resolution is about 1.5 arcsecond, but still this galaxy appear very extended with a diameter of at least 20 kpc, and this source is a redshift 3.25, so again belonging to this galaxy over density anchored at the same redshift of the quasar. The kinematics of this galaxy is again very smooth, indicating the presence of a rotating disk. And therefore, by combining, now we can start to combine, for example, the kinematics of galaxies in the field and start to perform correlation with the properties of the intergalactic gas, such as, for example, testing cosmological results for cosmological simulation, predicting the so-called spin alignment effect. Of course, the statistics now is still very low, but this is a good starting point. By looking at this galaxy in other wavelength range, since we have collected a lot of information in the whole electromagnetic spectrum, we saw something like that. This is an HST image showing a sort of ring of galaxies. It was very strange to look at the structure, but we know that in the rest frame UV, the dust obscuration play a significant role. And therefore, we went in JWST. And in JWST, what we found is the following thing. This is a super spiral galaxy with a diameter of about 30 kpc, as revealed by our JWST NIRCam observation. And here also reported contours of showing the red and blue part of the rotating disk as revealed by ALMA. And this is a gigantic spiral galaxy. It was totally unexpected to found at redshift 3. The diameter is about 30 kpc, so it's basically the Milky Way at redshift 3. Here is a pseudo RGB image of this galaxy that we call the Big Wheel. The results we published recently on Nature Astronomy this year. The paper got accepted just yesterday. You can clearly see this galaxy by eye from far in the field of the quasar. And this galaxy does not compare with the other population of galaxy at redshift 3 in terms of mass size relation. It is more similar to the expectation from the local universe, while it is forming stars at high rate, similar to indeed the redshift 3 galaxy. Therefore, this additional finding in this field is suggesting us that somehow high dense environment promotes the formation of large disk. And this is evidence like this are now coming in the literature. This is not the only giant spiral that has been found so far in dense environment at redshift 3. So stay tuned for further results about that. We are pushing further the investigation of this large-scale environment. Indeed, we acquired additional news observation showing that the filament is actually extended further on 8 co-moving megaparsec, at least toward the north and south part of these structures. We acquired the multi-slit spectroscopic observation with JWST, with multiple slits placed both on filaments to get H-alpha emission and therefore place constraint on the excitation mechanism of intergalactic gas, and also on specific galaxies such as the Quasar Companion, again, that revealed extended H-alpha emission that allow us to further investigate this interesting system. Another thing that we are going to do, thanks to a pilot program that has been recently accepted with ALMA, is to try to investigate the CGM Byron cycle, CGM galaxy Byron cycle down to innermost scale. And this program is briefly showcased here. We targeted this giant Lyman Alpha nebula, also exhibiting very extended carbon-4 and helium-2 emission. We also acquired extremely high resolution observation using Muse narrow field mode that is tracing the gas down to the innermost part near to the position of the quasar host. And we can therefore reliably trace the kinematics of the CGM gas surrounding the quasar, as you can see in this helium-2 velocity shift map. And we are imaging the field of this quasar using high resolution observation in order to try to correlate not only the kinematics of the interstellar medium within the quasar host with that of CGM, but also identify additional dusty star-forming galaxies currently undetected in the rest frame UV, and start to do correlation between spatially resolved physical properties of the CGM gas with that of the galaxy, in order to understand how galaxies get their gas from the surrounding medium, and which is how this complex mechanism happen, and how the galaxies are shaped due to the interaction with their surrounding medium. And this is the kind of investigation that we are going to do. So in the last 3 minutes, I will show you some brief results that we are obtaining by using quasars as a background probes of the intergalactic medium. So this is another interesting field that we mapped with ALMA. This is the MUSE Ultra Deep Field, which is providing extremely deep observation toward a field hosting a quasar pair at redshift 3. Is the same field that I showed you at the beginning of my talk, which also we discovered Lyman alpha emitting filament connecting these two quasars. And we used actually two quasars as our background sources, and we acquired also high resolution and high signal to noise spectra of these two quasars using UVES instruments. And we also mapped this field using ALMA. And we unveiled the population of dusty star-forming galaxies that are indicated by these blue squares. And these galaxies actually are interesting objects. They are very massive SMGs. Most of them lives actually in group, on which they are the most massive members. But very interestingly, the main results that we found by correlating the absorption features observed in the quasar spectra with the systemic redshift of these dusty star-forming galaxies, we found that they are very well aligned in velocity space with respect to the absorption features. Even if this is not the case regarding the impact parameter, because as I was showing in the previous slide, most of them actually lie far from the associated line of sight of the quasars, but still they are very near in the velocity space. Therefore, suggesting that these massive members probably occupy the gravitation, the center of mass of the gravitational potential well in which they are finding, and they are therefore good tracers of the large-scale structures traced in the absorption rather than the CGM surrounding them. We are pushing further this kind of analysis also thanks to a recent ALMA survey that has been completed, including 32 hours of observation, targeting systematically 10 quasar fields, part of the VLT large program, MUSE analysis of gas around galaxies, which provide magnesium 2 absorption toward this quasar field. And we are going to investigate with more statistics the role of these dusty star-forming galaxies on the cosmic metal enrichment. And with this, I think I will conclude with this slide, this summary slide, reporting the main question that I try to tackle in my talk that still require further investigation. And therefore, the take-home message is that now we are able really to bridge the scale from the physics of the interstellar medium in quasar host and surrounding galaxies through the large-scale structures hosting them, passing through the gas in the immediate surrounding, by studying the baryon cycle in the circumconducting medium of quasars. And thank you very much for your attention, and I'm happy to take any question if you have.
Thank you very much, Antonio. Very, very nice talk. So let's see if we can, we have questions from the audience. You can raise your hands if you have. Don't be shy. Any of the extragalactic researchers here, I'm sure they have some questions. Otherwise, I will ask one or two. No takers. Well, I will ask. So regarding the big wheel. Okay, Maria, we have one taker. I will
Hi.
hold my question for later.
Okay, sorry for the interruption. I would like to ask you about the slide number 38 that you say that the large amount of molecular gas enhance the star formation. How do you conclude that?
So slide 38, you said, right? Let's see. Okay, I went too fast now. Yeah, sorry. No, because it's a bit stuck. Okay, I can go directly. You are referring to the CO luminosity function, right? I guess you are referring to this plot.
Yes.
Okay. Yeah. Actually, so here the interpretation is actually not very easy. But so what we have done here is to compare the CO luminosity function that we found that we measured in our field that is reported in red and yellow in different redshift range. In this case, plus minus 4,000 and 1,000 kilometers per second, respectively. And we compare with that of blank fields, so associated to galaxy living in normal field. So you can clearly see that you can see an effect in terms of normalization that is suggesting us the presence of a huge overdensity of galaxy, this kind of difference normalization. And then there is this flattening. This flattening is meaning that there is a further excess in terms of more massive galaxies, because they are more rich in molecular gas than other galaxies. And this excess in this amount of massive galaxies is suggesting that actually somehow the large-scale environment is promoting the formation of a larger fraction of massive galaxies with respect to that is observed in blank field. This is the interpretation that we suggest. And yeah, don't know if I answer your question. I hope I.
Yes, thank you.
Okay, thank you for your question.
Actually, as a follow-up to that, do you have the luminosity function of the field like when selected based on the star formation rates? I mean, do you see these galaxies have just high molecular gas content, or they are also forming stars, or maybe they are just gigantic gas clumps that they are not yet forming stars? I don't know.
Okay, yeah, thank you for raising this point. So we actually have we didn't check actually the, let's say, luminosity function in terms of star formation, but this is actually interesting, and we should try to do it. Let's say that in this case we expect a similar behavior, since the molecular gas is actually associated to star forming regions. So we would expect in principle to see a similar effect. But what we have done actually is the luminosity function using the UV magnitude, for example, by using the Muse data. And what we found, we also published this work, I can give you the references if you are curious. And we actually didn't found such kind of flattening. We just found a higher normalization. Yes, but yeah, it's something that we should do. Thank you for this question.
Perhaps, but is the UV luminosity function corrected for somehow for extinction, or because you would
Yeah.
It is.
Yeah. We corrected for extinction. We also corrected. We estimated that the completeness, and we should. I think the next step is to try to also compare the different results that we obtained in different wavelength bands in order to give a coherent picture of what is happening in these fields in terms of star formation in galaxies, galaxy gas content, dust obscuration, so forth, so on. Yeah.
Okay. My question was about the big wheel, this massive Milky Way-like galaxy in this field, no? Right? I think.
Yeah, exactly.
So, do you? What is the gas fraction? Do you have the gas fraction? Because maybe I missed it. Do you have the gas fraction for this thing?
Yeah, so we estimated the molecular gas mass, of course, assuming some assumption on the CO423 to CO120 conversion factor and also on the alpha CO. And we actually have the gas fraction. I can give you the number if you are curious. That is relatively, let's say, if I have, I mean, you can find now this paper on the literature. So the molecular gas mass is 2 times 10 to the 11 solar masses, basically.
Okay.
While the stellar mass is 4 times 10 to the 11. So
okay,
is 50%.
So twice. Okay.
Yeah.
Because my question was motivated by, I mean, in order to have such a what it looks like such a stable disk, you need already a relatively low gas fraction, right? Otherwise, it would be unstable, and any disturbance of the disk would fragment it and just we wouldn't see it. I mean, the survival of the disk would be very small. But this, it's a bit crazy that can have this such a gigantic thing. Have you seen if models can predict this kind of galaxies at redshift 3? Such big, I mean, there are ellipticals at redshift 3, so I guess yes. But
exactly. Regarding the stability of the disk, we actually have multi-slit. I can show you some. There is a hidden slide here that I can share. Let's see if I'm able to share.
I guess you can calculate the dynamical mass as well, not from the rotating curve.
Yeah, so actually, since we have a multi-slit observation toward this field, we also placed 3 adjacent slits toward the big wheel to study its kinematic through H-alpha emission. And what we found is actually that the kinematics is overall very well consistent with a thin rotating disk with a high degree of rotational support, relatively high. So the maximum velocity over sigma is about 6. So still a cold rotationally supported disk, let's say. We found also additional non-circular components like this clamp that is probably that is associated to this clamp that you can see also here in the photometric image. And this is probably a minor merger galaxy that is penetrating the disk, but not affecting the overall galaxy kinematics. So overall, this galaxy is a rotationally supported this galaxy. Regarding the comparison with the cosmological simulation, we tried actually to do such kind of comparison. What we found is that these kind of galaxies are very rare, are predicted but very rare. So it's not, let's say, it's not an impossible galaxy. It's something that, yeah. We also calculate. I'm sorry, I cannot provide you the exact number right now, but in the paper we provide also the probability to find this galaxy in the field based on prediction from cosmological simulation.
Because it must have not experienced any merger during a long time in order to. It's like actually the contrary to ellipticals, right? In which
exactly,
you quench them via major mergers. This is a case where by, I don't know, luck or whatever, there are no, it's an isolated halo just forming a gigantic galaxy on its own. So
yeah, exactly. It's very interesting. But also there is another famous over density, a similar redshift that is called SSA 22. Maybe you already heard about this name. And also they are finding other objects like that in that field. And so it seems really that it's not by chance that we are finding these gigantic spirals in such a dense environment. And probably the interpretation is that somehow this large amount of gas reservoir surrounding this galaxy promotes the formation of large disks.
But in an environment that you wouldn't expect so, right? Because
because it's very harsh.
So
yeah, you
over dense
expect,
that you would expect a lot of interactions. But
yeah, indeed, it's very strange. It's very strange. But also the quasar companion that I was showing you before is another crazy object because it's just 10 kpc south the quasar. It is a monster, but is incredibly smooth in terms of kinematics. It's a super cold, dynamically super cold disk, and also very massive. The system is also very interesting because it seems that the quasar host is just a satellite of this other companion.
Yeah.
So maybe we are looking at a merger in progress.
Very interesting. Yes. Okay. I don't know if the audience there's anyone with some final question or doubt. If not, we can close it here and thank again Antonio for giving us this really great talk. I'm gonna stop the recording now.
Thank you very much.
Okay.